So we're on page 198 looking at the first few problems here. Find the extreme values and where they occur. So essentially we're looking at where are the min and the max for our particular problems. So number 2, we've got a little graph here, and I see it looks like at -1, 0, we've got a filled in circle. At 0, 0, I think it's filled in, and then at 1, 0, it's filled in, and then at 0, 1, it's open, and at 0, -1, it's also open. So we're looking for our min and our max values for our function, but we can't have an extreme value min at an open circle. So our min is going to be at -1, 0 because that's the value that is like filled in. That's like our lowest value. Because if you look, that line is like going up, and then there's like a jump, and then we have it going up on the other side. So then our max is at 1, 0, because that's where it's filled in there. And these are technically called local maxes and mins for the given problem, because most likely this problem continues elsewhere, but that's just the part that we can see right now. So I've got, looks like they're all filled in, so I've got it going like down, and then it's going spiking up and then coming back down. And so we can have multiple mins and maxes that are like local, but we can only have one that's absolute. But in this situation, we're just looking for essentially our local mins and maxes. And so our min values would be at 0, -1, and then the other part where it's coming down and it stops would be at 2, 0. And then our max values are where it's at its highest point, or like where it's like turning around, and so that would be at -3, 0 and at 1, 2.
How come there's like 2 points for this one?
Because the local mins and maxes are every time essentially the graph like turns around. So like how it's coming, it's like going down, and then it's like going up, and then it's coming back down. So this is a min, and this is a max. But then there's stoppers here on the ends. So this was a max, and this was a min, locally. But absolute, this one, well, I don't know what else was the graph was doing, because this is all I can see. But if all I could see was this, and this would be my absolute max and my absolute min. But I'm just looking for all of the maxes and mins right now. So every time essentially like the concavity changes, we either have a max or a min. Like the highest and the lowest that it can like go to. And honestly, like, I don't love these ones for seeing that. It's kind of like just like a very like basic thing. But I think it's honestly easier to see in problems when we're like solving mathematically, which is ultimately what they really care about you being able to do. So identify each x value at which any absolute extreme value occurs. Explain how your answer is consistent with the extreme value theorem. Let me see if I can find. The extreme value theorem says if f with the function is continuous on a closed interval a to b, so essentially we'll see all of these, well, most of these have a closed circle on both ends, showing us that that's our interval. Then the function has both a max value and a min value on the interval. So, looking at number 6, and it's possible for some of these that the extreme value theorem won't apply, so we'll have to pay attention to that as well. So we have at A something, we have a point, and then we have a continuous function all the way to B something. We don't know what the B value or what the Y values are. All they care about is X values for this. And so it's a continuous function that is on a closed interval because we've got it closed in. And so I'm looking for the max and the min value. So this is like one max and one min because it's the extreme value theorem. So it's the most max and the most min value is what we're looking for out of what we can see. So our max would be at roughly x equals c. And then our min would be the most min value. So I have two local mins here, but I have one that's like the absolute extreme one that I'm looking for, which is at x equals b. So it's a closed interval, and so because it's a closed interval and it's a continuous function, my extreme value theorem applies, so I have to have a max and a min, essentially, is what I need to say with this one. So extreme value theorem applies, so both max and min exist. If I look at 8 though, I've got a function that's coming down. It kind of looks like part of a parabola, but it has a lot of open circles in there. I see one of the open circles has a closed circle above it, but I notice this isn't continuous because it has points of discontinuity in there, so that's automatically an issue. And it's also not defined on a closed interval. So if it had like closed circles on the ends, but then it had that hole in the middle, it would be how do I say it? It would be like defined on the closed interval, but it's not continuous because of the hole. So this one is not continuous or defined on a closed interval, and so this one, the extreme value theorem does not apply, and thus there's no max or min for this one. Let's see, with this one, number 10. So I've got essentially what looks like, the birds that people draw, and then I've got an open circle on one end with a closed circle above it. And then I do have a closed circle on the right end of it. So this one, we can have max and min values even if the extreme value theorem doesn't apply. The extreme value theorem itself may or may not apply. So this one, what I notice is it's not continuous. So the extreme value theorem doesn't apply, but I do see a max and a min because we've got the closed circles on here. The previous one, number 8, didn't because we had open circles all the way across, so it didn't have any maxes or mins because it wasn't doing anything. But for 10, we will have a max and a min. No, that just happened. Just lost a cow. So the max is going to be at that closed circle value at x equals a. And then the min is going to be at the point where it comes down like the middle of the bird, so at x equals c. But the extreme value theorem does not apply because it's not continuous. All right. So getting into some of the actual problems here. Use analytic methods to find the extreme values of the function, aka max and min, on the interval and where they occur. Identify any critical points that are not stationary points. So let me find, just as a refresher here. So a critical point is a point in the interior of the domain of a function f at which f prime of 0 equals 0. So we're going to find the first derivative. I don't think for what we're doing we need to find the second derivative, but normally like in that step 1, I usually go ahead and find both, but I'm not going far enough in these problems to need to do that, so I'll probably just do the first derivative for time. And then basically from there we set that equal to 0. And so it occurs, a critical point is either where the first derivative is equal to 0 or does not exist. A stationary point, though, is a point in the interior of the domain of the function f at which the first derivative is equal to 0 that can be a max, a min, or an inflection point. And an inflection point is where the concavity, the second derivative, changes. So we'll look at, I think my page is all mixed up here. Anyway, so we'll look at that. All right, so 12, g of x is equal to e to the negative x. And we're on the interval -1 less than or equal to x less than or equal to 1. So a lot of times when they give me my interval in this way, I rewrite it as like -1 to 1 as like a closed interval that way, just for the visual for me to see it. So my first derivative, so my essentially step 1, is find the first derivative. So g prime of x would be equal to what? See if you remember. Negative e to the negative x, yep. Or if I wanted to, I could write this as -1 over e to the x as well. Doesn't really matter. Honestly, I probably will end up using the first form that you had, like the way you said it, because it'll probably be easier to see. So now I'm going to check at the endpoints. There are, well, let me do this. Is there anywhere that this is equal to 0? Like that the first derivative is equal to 0? Is there any value that I can plug in for x that's going to make that equal to 0? No. So I don't have anywhere that that's happening, so I then am using the endpoints. So you typically end up checking the endpoints if they've given you an interval, and then you check your places where it's equal to 0. So that's a little bit different because the previous problems that we had done the other day, they did not give us an interval. So we had to find our critical points by setting it equal to 0. So we only checked those. But because they're giving us a closed interval that we're looking at, I'm now going to use the endpoints as well. So if I had critical points, then I would use those and my endpoints. Which we should be able to see that in a different problem in a second. So g of -1, I put in -1 for x, so I have negative e to the essentially positive 1, because negative is positive. So then that is negative e. I'm going to go ahead and do the other one, and then we'll talk about max and min. And then g of +1 is negative e to the negative x. Oh, I know what I did. I need to backtrack. This is going into the first derivative. I'm trying to plug it into the derivative. So I need to get rid of the negative sign. This is the part that's hard. So I'm going to make a note here. Plug into original. To determine if it's our max or a min, we plug that value into the original. So I would have, that would just be a positive e. Then down here, e to the negative 1 would be obviously just 1 over e. What is happening here? Hold on. Expecting one of these to be positive and one of these to be negative. Oh. Because this one's different. All right, so if you look at the local relative extreme values here, let C be an interior point of the domain of the function. Wait, this is not the endpoint. I need this one. It's the endpoint. Where is what I'm looking for? No, I do need this. Okay. So let C be an interior point of the domain of F. Then f of C is a local max at f of C, or at C, if f of x is less than f of C for all x in some open interval containing C. It's a local min at C if and only if f of x is greater than or equal to f of C for all x in some open interval containing C. But then it says a function f has a local max or local min at an endpoint C if the appropriate inequality holds. So this is also the same for the endpoints, not just for the interior points. So it would have been like if we had a critical point, this is also true for the endpoint values that we're using, which is why it was different than the ones we did the other day. So that means that I have a, let's see, comparatively to the original function here, then this one has to be the max, bless you, at x equals -1, bless you, because f of x is less than or equal to f of C, because this is just e and that was e to the -x. And then this one is a min at x equals +1, because that is less than that value there, or greater than that. Wait, yeah. This is less than this, so it's a min value. This is why I think I like the other notes better. Where are they? Let me go back. Stuff is all out of order. Hold on. Okay, yeah. We have to do it this way if it's the endpoints. If it's a critical point, then we can use the second derivative test, which makes it a whole lot easier. We usually have a critical point when we're doing them, so we'll look at that in the next one, and we may need to come back to this one to look at something else, but we'll hold there for right now. All right, 14. K of x is equal to e to the negative x squared from negative infinity less than x less than infinity. So this one, I'm not going to be able to use my endpoints because it's from negative infinity to positive infinity, so I'm going to have no other choice but to have critical points essentially. So I'm going to go ahead and find the first and second derivative here so that we can do this one like the ones we were doing the other day, where we're finding the critical points and then finding the maximum that way, because those ones are way easier to find, and this is typically more likely to be what you have. So the first derivative would be what?
Negative 2x e to the negative x squared.
Yep. And then over here on the side, I'm going to do the second derivative of that then. So what about the second derivative here? Because now I've essentially got a product rule with my chain rule.
Negative 2 So the product rule is, oh crap.
I'm basically working with these two things being my two terms.
Yeah.
So the product rule would be the derivative of the first, which is the negative 2, times the whole second piece. And then plus the negative 2x times the derivative of the second piece, which is what you had just found. So a negative 2x e to the negative x squared. Kind of ran off the paper, so I need to smush it together. So then that's going to give me negative 2 e to the negative x squared plus 4x squared e to the negative x squared would be what that ends up becoming once you multiply it all through. So this would have been my step 1 from the other day. So then the step 2, try to find the steps in order. We're finding the critical points, which is where the first derivative is equal to 0. So we would have negative 2x e to the negative x squared equals 0. So there's essentially, I can either break this up into two separate pieces, but there's no way for this e to the negative x squared to be equal to 0 for the same reason as the first part. So I essentially can divide by 2, and I can divide by this because there's no way for that to be 0. So I've got negative 2x equals 0, or e to the negative x squared equals 0. Well, that's not possible there. Divide by the 2 here. So then x equals 0 would be my critical point. And so then evaluating my first derivative, or well, I don't need to do that. Yeah. So then step 3 is to determine then if they are mins or maxes. So the first derivative, so k prime of 0 is equal to just 0, I guess, right? Equal to 0. So then the second derivative evaluated at the point, at our critical point, is negative 2e to the 0 plus 4 times 0 e to the 0. So this second part all goes away. And so the second derivative at 0 is just going to be equal to negative 2 because this is 1. So that's equal to negative 2. To determine if it's a max or a min, we look at it compared to 0. This is less than or equal to 0. And so then that means that it's a max using the second derivative test. And so then it has a max of, if I plug that in, k of 0. So if I plug in 0 to the original, I have e to the 0, which is equal to 1. So what I can then say is I have a max of 1 at x equals 0, which is what I'm ultimately trying to find. Now I think trying to see if the second derivative test would have worked on the previous problem. I'm gonna see really quick. So the second derivative of this would have been just a positive e to the negative x. Plug in negative 1, I would get e to the 1. Plug in negative, get e to the, e to the negative 1. Yeah, that's why the second derivative doesn't work with this one, because it doesn't give you 1 is greater than 0 and 1 is less than 0. So we have to use the other method. Okay.
I have no idea, like, why we did any of that.
Where, on this problem?
Yeah, on 14.
Oh, 14. Which part?
So, why did we get the second derivative of k?
Because that's using the second derivative test to help me determine if it's a min or a max.
And then, like, why, when we did the step 3 of k double prime, why did you put it like negative 2 is less than or equal to 0?
So essentially I was finding the second derivative. So negative 2 is the second derivative value. So this is k double prime of 0. So then to use the second derivative test, I'm saying, is this value greater than 0 or less than 0? Because technically equal to 0 means something totally different, and that's when we have to use step 4. So since this is less than 0, that means that's a max. So it's opposite of what you would think. If the number is less than 0, it's a max. If it's greater than 0, it's a min.
So if it's less than 0.
It's a max in the second derivative test. Which technically, part of the problem, or the reason the way the book's doing the things the way they're doing, is they don't actually teach you the second derivative test until um 5.3. So they're assuming you don't know that yet, which is why we had to use the other method in the previous problem, because the second derivative test didn't work for that problem.
Well, yeah, what did we do for that problem?
So that problem was, let me find where it is. Was this stuff in your notes, the local extreme values. So let C be an interior point of the domain of the function. Then f of C is a local max if f of x is less than or equal to f of C for all x in some open interval. It's a min if f of x is greater than or equal to f of C.
Okay.
So essentially it's a similar thing, but this also applies for the endpoints, which is what the notes go on to say. And so this value essentially evaluated at each endpoint, we're looking at, is it less than or greater than the original value? So this is a max because this is greater than, or wait, I'm saying it backwards. Because this is f of C. So this is, this is greater than the original. So it's a max. These ones are opposite. But I'm also, if you look at your notes, it's f of x compared to f of C, or I'm actually saying them backwards. So I'm saying f of C is greater than f of x.
Yeah.
Whereas on the other one, f of C is less than or equal to f of x. And so that's where I got the min for that one from. Because technically this is essentially the same thing here. Because that's just 1 over e to the x, basically. And this is just 1 over e. So unless e is 0, then that's obviously going to be less than that.
Okay.
Those ones are much more confusing, and pretty much everybody will tell you they prefer the second derivative test. This particular problem, the second derivative test did not work. Because, again, once we'll get to 5.3, you'll see there are certain situations where it doesn't work. But there's others where, like, it will as well, outside of just this situation that we're dealing with right now. The more that we, like, go through them, I think it will make more sense, though. Because, like, with the next one, well, let me see. Well, yeah, let's just go ahead and look at 18. So the first one, we had a closed interval. This one, we had a purely open interval because it was negative infinity to infinity. This one, we've got f of x is equal to x to the 3/5 on the interval -2 less than x less than or equal to 3. So the first derivative would be what?
3/5 x to the negative 2/5.
Yep. So we're looking for where that's equal to 0. Where's the only place that's equal to 0?
X is 0.
Yep. So when x is 0, that's 0. So that means that that's a critical point. So I'm going to be checking my critical point, but I'm also going to check my end point here of 3 because it's on, that part is closed. So yes, it's a half open interval, but I'm only checking the 3 value. So into the original, we have f of 0 is equal to 0. Checking my endpoint value, so that's the critical point. Checking the endpoint, we've got f of 3 is equal to 3 to the 3/5, which essentially is the same thing as the 5th root of 27. Which is greater than my initial value. So this is a max at x equals 3. And I guess I should say of the 5th root of 27, technically.
So, how do we know that it's greater than the x?
Because if I choose any point in here,
Oh, okay, that makes sense.
then it's gonna be.
Yeah.
It's essentially like choosing a point inside of your interval.
Okay.
So like it was a little bit different, obviously, with this problem. We used the second derivative test because it was closed or open interval. Up here, if I chose like 0, well, e to the 0 is just 1. So this was, hold on, f of that was less than this value, which made this a max. F of 0 was actually equal to this, but it can be less than or equal to or greater than or equal to on these ones, and so that's what made this a min.
Yeah.
And then down here, choosing a point in there, like pretty much any point you want, but if I put 0, then I get 1, which is less than this value, and so then that has to be a max.
So is there no min for this one because it's like open on the left?
Right.
Okay.
Yeah, at least there's not a min that we know of. The critical point produced 0, which basically is just neither. That would be the situation where we have to look at like something totally different, and you don't know how to do that yet, technically. That's because the thing about it is, and I kind of forgot that that's what happens until we get into like doing problems, but basically 5-1 and 5-3 really go together. So as we did the notes for 5-1, I've already given you a lot of the notes for 5-3. Which I think if you look, I think 5-3's notes are relatively short, like comparatively to like this one was like really long. Because that has stuff like the second derivative test. So like I kind of reiterated in the notes for 5-3. And it talks about points of inflection and some other stuff that we've already briefly hit on in these notes, because the notes that I classified as easier to understand notes came from the AP prep book, which is very helpful in seeing the big picture, to see everything at once. So that's why 5.1's notes are so long. But like you don't know the second derivative test yet, so they're using a different method altogether to find them. So if you look at like the book examples that they have like leading up to stuff, where you're like finding the mins and the maxes. So like on like example 3 on page 194, like you're gonna see them testing stuff, and then they're showing you like what it's equal to, and then what like the endpoint value is, to show you how to determine like if it's a min or a max. Versus we would use the second derivative test. But on the exam, I would overall use the second derivative test unless it's one of these where like you can't.
Yeah.
Because a lot of them aren't giving you an interval. Like you're stuck with just a function, and it's like, all right, find this. They've shortened, because obviously this is a function that goes on forever. They've said just look at this part of the function, and that's not normally what they're going to give you. So we'll stop there for now. Tomorrow we'll pick up, we may go back and reiterate a little bit of this. But to look at a few things here, and then look at a couple more problems, and then essentially you'll just have some time to work, but finding like extreme values and where they occur, because again, a lot of this is easier to see with the second derivative or some of those other things that you don't technically know yet. So a lot of these problems, while they're hard, they're not like as hard as what they will be. So we'll probably honestly just be maybe 1 or 2 more days on this, and then we'll be on to the next thing, because then, like I said, so we might end up getting all the way to 5.3 just because of how it like ties together. 5.2 is not nearly as bad though. 5.2 is relatively easy. It's like 5.1 and 5.3. It would be nice to get through 5.3 because 5.1 and 5.3 tie so much together that
Yeah.
I kind of wish 5.3 was actually section 2, but there's a couple things in section 2 that can be helpful. So anyways.